We have jumped around a little. In the manual, there was the first 50 or so pages revolve around the possibility that you have different I/O, a different processor, a different hardware structure than what we used to create the manual. At this point, we're going to tidy that up just in case you've gotten off track, didn't save all of the projects. So we're going to get everybody back to the same point. And what you see in front of you is the beginner LXX. Now, I have it L31 because I'm using an L31 processor. If you're using an L23E, then you would have L23E in the names of your project file. So beginner L31. In this case, I saved it as aliased IO, which I had you do in the manual. And in case you have forgotten how to alias IO, because we have not done a lot of it, if you type in a name for a tag, we'll just give it any old name, junk00, and over here is your alias for column. Now if I click here, it will bring up a drop down list arrow, but if I click right here, it will bring up the drop down list arrow and open the drop down list. And I want to alias this to some tag that already exists. In this case, we want to alias it to an IO tag. So O for output, I for input. We'll alias it to an output. Click on data. Now another thing you could have done, when this pops up, you can click here, or you can go all the way over here and try to hit the right spot where you hit the drop down arrow and you use one less mouse click. That's not necessary. And then pick a bit. Okay, then hit enter, and there you have it. So this is not a legitimate tag for our project, but these are. We're going to use these tags. The next section is controlling the data files from your keyboard. From here on, we're not going to focus so much on variations in I/O, but get down to business with learning programmable controllers and learning RSLogix 5000 and learning the Logix engine all combined. I had you put the key switch on your controller into the run mode. On your controller, there's going to be a key switch or a toggle switch. There's going to be a key switch, and it has 3 positions. If you look up here in the online toolbar, you see the key switch right here. But because we're offline, RSLogix 5000 does not know what position that key switch is in. That's why it's displayed kind of grayed out, and you don't see anything selected. That key switch you want to put over here into the left-hand position. That's the run mode. Okay, so right now the processor's in the run mode. We're going to select communications, who active, wait until we make sure we see the processor, and then we're going to select download. And we're going to demonstrate what we demonstrated in the manual with a little discussion. And that is, if the key switch is not in the middle position, or at least in program, you're not going to download. You cannot download to a controller that is in the run mode. You see here we get a message, the key switch is in the run mode. Move to remote or program in order to download. And you see download is grayed out. We had you flip the switch to the middle position. Now, by the way, we are actually online with a controller. I mean, we're not totally online, but at least the status, if you look over here at the online toolbar, you can see the key switch is in the run position. We've established communications with the controller, and remember, RSLogix 5000 would have to know what's going on with that controller before it can download. Otherwise, it wouldn't give you this message, the key switch is in the run position. So it knows it's in the run position, so it displays it. Now watch this key switch and that message when I put the key switch in the middle position. You see up here, now it's in the remote position. This is the key switch position, not the mode. This is the mode. And now you see it says the controller is in the remote run mode. Click download, and we'll wait. And we started in the run mode, so it's going to ask us if we want to go back to the run mode. If you started in the remote program mode, it wouldn't ask you that question because there's not a safety issue involved here. Keep in mind, if you download to a Logix engine controller, as far as that is concerned, any controller, it's going to take it out of the run mode, which means the machinery stops. If this is a running process, meaning this controller is controlling a machine, a process, everything will stop. That can create conditions that are unsafe for startup. That's why you get this question. Done downloading, change controller mode back to remote run. We're going to say yes because we don't have a machine. But if this were an actual machine out there and you went right back to the run mode and it picked right up, you may have had cylinders relax that had the air pressure removed, and so weight on them by gravity moved them to a different position. If you start back up, not only might you damage the machine or process, you might injure a human being as well. Okay, so we're online now in the run mode. And what we had you do was to go to the controller tags, which that's where we're at. I had you expand local slot 1 I for input. I had you go to the monitor tags, and of course when you do that, it doesn't necessarily leave it in the form that you had it when you go back and forth. See? Go to monitor tags. Mainly what I wanted you to see was this. Now the one that we're showing in the book is for the IQ6XOW4, which is what we have here. So what's in the book and what you see here is somewhat identical. Now we could have pulled out this until we don't see any more truncation of this double integer. That's a 32-bit double integer. Our actual data is a single integer, an 8-bit word, that's displayed here. And you remember that I had probably toggled that input on some other time. So I see that there's a 1 right there, which means that input 2 is on. So I go over to my digital field device simulator and I turn it off, and you see now that those are all zeros. The reason that we opened this up is because I wanted to compare it with the module defined tags. We've done this before, but I want to do it again. So we opened up the instance of this tag right here. See, it ends with I and 0. So we go over here and double click on that same class of objects, and then we had you compare, and this is not easy to do. I see we had a few things open there that I didn't realize was open in the background. And you can follow along if you want. You can pause this video and give yourself a chance to get this set up. I didn't have you do this in the manual. I just gave you images of what you see here. Okay, so here we have the name of the class of objects. This is the class of objects right here. And then we see we have fault, data, and readback. Here we have fault, data, and readback. They're not in the same order. This is alphabetical order here. This is not. Obviously, D comes before F. It was the order in which they created the members of this module defined data type is what you see here. But when the tags show up here, they're going to show up in alphanumeric order. That's why they're in a slightly different order. Nonetheless, it doesn't matter. You see that local 1I has a single integer data, a double integer fault, and a readback single integer. If you look over here, you see the same 3 members. This local 1I is an instance that you created of this data type, this module-defined data type. And we had you repeat that to look at some of the other data types as well. If you don't make the correlation between these two, I mean firmly, right now, I would just keep going back over and over this again, playing with your graphical user interface that you're looking at right here, and looking at the information in the manual until you firmly understand that this tag right there is an instance of this data type right here, this module-defined data type. And again, we have, I'll collapse this down, we have this class of objects up. We can open up another one, the configuration, and you see here we have an integer, a Boolean, and 4 single integers. We have the exact same thing right here, same names as here. Whenever you use a user-defined data type, or a predefined, or a module-defined, when you create an instance, it's always going to show you the data type and the structure in your tag database. So you see the configuration tag's the same. We'll open up the output, and of course there's nothing to the output, it's just a single integer. Also in the manual, I gave you these side-by-side comparisons. And then I said in the illustrations below, which is the class of objects and which is the instance. Well, we just went through all that. It says light gray is the class instance, the darker gray is the class instance. Well, I'm looking at the way that this was printed, and the light gray looks white and the darker gray looks just light gray. Well, obviously, from what you've seen in front of you, the gray, in other words, you're looking at the structure in one where it says members in your manual, step 15 or whatever step it is, roughly page 73, 74. On the left-hand side, it says members. Well, members are members of that module-defined data type. And then over on the right side, in a light gray, you have local 1C, local 1I, and local 10. Obviously, those are the instances. And again, I reiterate, if you don't understand this, if you can't correlate an instance to a class of objects, you need to keep working on that. It might behoove you to go online on your search engine, your favorite search engine, and type in information objects, information object modeling, classes of objects, instances of classes of objects. See if you can find a good readable document that explains the difference between a class of objects and an instance of that class of objects. We also, in the manual, have an illustration of the IQ6XOW4, and we correlate what you see on the screen here, in particular for inputs and outputs for the data. These bits right here for inputs and these bits for outputs, we correlate those visually to screw terminals on that module. And we specifically stated when an input circuit senses current flow greater than 1.5 milliamps, because remember, the solid state input circuitry has an off state and an on state. The off state is not necessarily zero, but it is anything below a certain threshold. In this case, 1.5 milliamps. So that's basically 1500 microamps, 1.5 thousandths of an amp. When the input circuitry senses current flow greater than 1.5 milliamps, the corresponding bit in memory goes high. The state changes from 0 to 1 if the processor is in the run mode. Now that's not necessarily true for inputs. That is for some controllers, but in this case, if I put this in the program mode, and you see the key switch here says program, it's not in remote. I could flip it back to remote, it's not going to make any difference. But if I flip on an input, you see it changes to a 1 here. So I'm going down and turn these inputs on to show you that in the program mode, then this is with the Logix engine, not with Slick 500 and MicroLogix. Inputs are updated regardless of the mode of the controller. Now I'm going to put it back in the run mode, remote run mode. Then also in the manual we stated that outputs, when a bit in memory location local bit 0 through 3 goes high, the state changes from 0 to 1. The corresponding output relay contact closes if the processor is in the run mode. Now that is true. We're going to cover this in our lab, but as long as we're right here, I'm going to show it to you. You're going to see it again when you do the lab. So we're looking at the inputs here, and we see the inputs update whether you're in the program mode or the run mode. The outputs, however, whatever this state of this bit, it won't actually go out to that output device unless you're in the run mode. To prove that, I'm going to put it in the program mode, actually the remote program mode. I'm going to change this bit to 1. I turn that bit on, but although I turned it on and the bit in memory is on, the output is not on, because this data image right here does not get transferred out to the actual card, the I/O card, unless you're in the run mode. You can change the state of the bits that are used to correlate to the outputs right here. Local slot 1 output data 0 through 3. You can change these to any state you want when you're in the program mode. Then when you go into the run mode, the processor takes over. Now in this case, we don't have any logic in there. So watch what happens. I'm going to go back to the run mode. Okay. Now the 1 stayed and my output is on. When I look over at my digital field device simulator, I see that output on. Why did it stay on? Well, there's no logic to tell it to turn off. However, if we did the same thing with an input, doesn't matter what mode you're in, you cannot, we'll turn this one back off. Okay, I'm going to go up here and turn this one on. Watch what happens. I put in 10 instead of 1. Okay, notice that it doesn't stay, because as fast as I can type in a 1, the controller's memory is being updated automatically by that input card, whether the controller's running or not. So I type in a 1, it goes into memory, but then microseconds later, when the I/O card has updated the memory of the controller, all those inputs are off. Consequently, if I were to turn that input on, see now it's a 1. If I put in a 0, it puts the 1 right back in there because the actual input is on. So remember that difference between the inputs and the outputs. Specifically in the manual, roughly on page 75, 76, 77, in that area, switch your controller to the remote program mode. All LEDs should be off, meaning that there shouldn't be any outputs on your hardware, at least the ones that we're working with. Then I showed you local 1I data and local 1O data side by side. In other words, I showed you these 7 bits right here and these 7 bits down here, but I showed them side by side. And it says type a 1 into this field, which we just did this, but we'll do it again. And then it says, did the processor memory accept the value of 1? You could answer yes or no and be correct in a sense. The answer that we wanted was no. And that's probably the answer you put. But if you're a computer science major, you probably know that the 1 did make it to memory, albeit it might not have been there any more than less than a microsecond. And it was written over immediately by the actual state of the input. Switch the processor to remote run and repeat the previous step. So we put it in the run mode. We typed in a 1. Did the processor's memory accept the value of 1? No, it didn't. the behavior between program mode and run mode was the same for the inputs. Did the processor's memory accept the value of 1 in the remote run mode? No. Why? And the answer is because by way of your keyboard, you have access to all these bits in the memory of the controller. You are directly communicating with the memory in the controller from this screen. However, the input module has module-defined tags so that it updates at the requested packet interval. Remember back here, we probably didn't look at it. Connection. Requested packet interval is 20 milliseconds. I said microseconds, and it could be less than a microsecond, but it's going to be at least as fast as every 20 milliseconds. That card is going to update the memory in the controller that you are looking at right here. Switch your controller to the remote program mode. You don't have to use the key switch. You can go up here and just hit program mode, and it's the same as flipping the key switch. The key switch shows the position. This shows the mode. So even if I flipped it over to program, see right there, program, and back, it's still going to say remote program, and the key switch will be in the remote position. This won't say remote program. It just says run remote or program. Switch your controller to the remote program mode. Type a 1 into this field. Now that's this field down here. Did the processor's memory accept the value of 1? Yes, it did. Switch to remote run mode while watching the memory bit and the output device that you have wired up to the output, or the LED for the output module. So go up here and we'll go back to the run mode. Now you see that this did not change, and the output did come on. Consequently, we also showed you these bits down here. So if you look down a little bit further, see this is local 1 output data bit 0. That output is on. And look down here. Output 00 is on. Because remember that this tag is an alias for this tag. So this tag really just points to this tag. This is the tag that's doing the work. This is the base tag. This is just a pointer or an alias. But notice that they're both on. And it did ask you, did any of the actual outputs or module LEDs energize? Yes, they did, because when you went to the run mode, part of the execution, the executive software, part of the execution is to take these, the state of these bits right here, and send them out to that module. Now there's only 4 outputs, so these other 4 are kind of hanging in the breeze, but they do go out there nonetheless. If any of these are in the state of 1, then those outputs are going to turn on. If I go back to the program mode, see now we're in remote program, they stay on. Here's the difference. With the inputs, from your keyboard, you're accessing these input bits. That's what we'll call them, input bits. You can change them, but every 20 milliseconds, the actual state of the field device simulator is going to change them to whatever it is, every 20 milliseconds. So really, you can't keep up with this. So these are always going to reflect the actual voltage at the screw terminal on that input module. However, with the outputs, the only time that the output screw terminal reflects the state of this bit in memory is if you're in the run mode. Now in this case right now, it's 1, but that's because the last thing that this was told was that it was on. This bit is on, but the output's not on. Okay, remember we're in the remote program mode. That bit is on. If I go back to the run mode, then my output comes back on, but you saw no change here. There's nothing in the program, because there is no program, to tell this bit that it's on or off. So if you turn it on, it stays on. If you turn it off, it stays off. Run mode, program mode, it doesn't make any difference. With no program, no code written, if you change the states of these bits from your keyboard, they're going to stay and remain that way. If you put the thing in the run mode like it is right now, whatever state these are, those outputs, that's the state they're going to be in. If you had a program in here that was turning off this bit, you went to the program mode, turned it on, it's on. But when you go to the run mode, the logic will immediately execute and write a 0 to this position. In the manual, I had you write a summary of the relationship between input circuitry of an input module and the output circuitry of an output module as it relates to the processor's memory locations. And we just went over that. Okay, we have seen what influence you have over the bits in memory associated with the screw terminals of input and output modules. The source for this data was an ASCII keyboard via USB to your computer's I/O chipset as a feature of RSLogix 5000. I decided I'm going to throw in something here that was not in the manual. It's jumping ahead, so I'm going to have you do something, or I'm going to show you something. You don't actually have to do it. I'm going to show you something. If you do actually follow along and do what I'm going to do next, you will have to delete it before you go on in the manual. So I'm going to close down the tag database here. I'm going to open up the main routine, and you see that because it's empty, if you open a routine and it's empty, it automatically gives you a new rung. The E's mean that it's in the edit mode, because it assumes you wouldn't have gone there unless you were going to do something. The only thing you can do with an empty routine is start adding logic. So there's our rung. I'm going to delete that. Okay, and then I'm going to add it back in from this toolbar up here. Now what I want to do is to create two rungs. The first one, I'm going to use the module defined tags directly. So that is the bit in memory that's controlled by that input. I'm in the run mode, so if I turn that on, see, it changes state. It's on, it's off. Okay, now remember that these are instructions that read the state of a bit in memory. They don't write it, they simply display whether the bit is on or off. So if you see it highlighted like this, it's on. If it's like that, it's off. Now this instruction is a true if on. So this instruction becomes true if that bit is on. However, that bit is off, so this instruction would be false. But that's not what we want to demonstrate here. I'm going to add another instruction, an OTE. We'll drill down, double click, drop down the list, go down to the output data, and I'm going to pick bit 0 of the output. We're online. I'm going to do a finalize all edits. This is a generic warning that comes up every time. So I'm not going to take the time to read this. I just want to finish this rung. Now, watch this. When I turn this on, this will be true and it will turn on that bit. See, if this is true, then it turns on that bit. Now, I'm going to select that rung, go Control C, Control V. You could have right click, copy, paste, you could have done it the long way. Now what I'm going to do is I'm going to replace this with input 0, the nomenclature. And I'm going to replace this with output 0. Finalize all edits. That is a tag, and this is a different tag. IN00 is a different tag than that tag. However, notice that because IN00 points to this tag, which is the same as this tag, whether you're using the module defined tags here directly or indirectly with an alias, it's still the same thing. This is the tag that's doing the work. Local 1i data 0, local 1o data 0. I thought I would throw this in as an added illustration of the relationship between tags. I'm going to delete. Now I'm doing this online. Finalize all edits. You're going to begin your ladder logic writing in the offline mode.